Next, we are going to consider in this lecture number 12 the variance and the mean square error of an estimator, the second measure of quality of estimators. Again, we start with the definition of the estimation error x tilde as x minus x hat, the difference between the true value and the estimated value. And we define the estimator's variance or mean square error as the variance of x hat if x hat is unbiased and x is non-random, because the x hat's mean, the mean of x hat, then is the 2x, which means the x tilde will be zero mean, and this will be the variance. Expected value of the error squared, x tilde squared, will be the variance. Otherwise, it will be the mean square error of x hat, and this does include the biased situations. And the expectations are to be taken over the measurements if it's a non-random parameter, and over the measurements and the parameter if it is a random parameter. But in any case, in the literature you'll see some confusion in the terminology. The mean square is sometimes called the variance. It doesn't really matter. But we have a criterion that does measure, and if we call it mean square error, it's a good measure of the quality of the estimator. The square root of the variance or of the mean square error in the more general case of an estimator, sigma x hat, which is the square root of the variance of x hat, is called the standard error or the standard deviation associated with the estimator, or the standard deviation of the estimation error. The way this is useful as a measure of performance is the fact that it provides a measure of the accuracy of the estimator. If we think along the lines of a Gaussian error, then the difference between the estimate and the true value will be up to 2 standard errors with 95% probability, because that's the deviation between the estimate and the true value, up to 2 sigma, with 95% probability, obviously. Now, let's compare two estimators, the maximum likelihood and the maximum a posteriori. Remember, the maximum likelihood has no prior information about the parameter. It's an unknown constant. It's a non-Bayesian approach, while the maximum a posteriori is going to use some prior information. So our intuitive expectation is that there would be some advantage, and we can quantify this in a moment, that the map estimator will have over the ML estimator. So the qualities of these estimators, as we discussed before, from a single observations quantified by the variances, will be compared. The maximum likelihood estimator in the case of single measurement z x hat ml was exactly z, therefore the variance of x hat ml, the expected value of x hat ml minus its mean, that's the true value, squared, that was equal to sigma squared, because z minus x0 was just the measurement noise. So we now have the variance of the first one for the MLE. Now the map, the maximum a posteriori, where we used a Gaussian prior, if you remember, was a weighted combination between the prior mean and the observation. And we are writing now the observation z explicitly as x plus w. And these are the two weighting coefficients which sum up to 1, minus the true value, which is denoted by x here. Sometimes we use x0, sometimes we use x. Right now x is okay. And what we have is, after rearranging the terms, we will have an x bar minus x here, weighted by sigma square over sigma 0 square plus sigma square, and a w. This will be, after taking the square and expected value, the prior variance sigma 0 square, and this will be the variance of the noise sigma square. Carrying out these operations, which suggested that you follow the derivations, or reconstruct the derivation from the third line to the fourth line, it will yield the, again, parallel resistors formula is sigma 0 square over sigma 0 square plus sigma square, which is less than sigma square, which is the variance of the maximum likelihood estimator. So the map estimator is superior in terms of variance over the max likelihood estimator because it uses prior information. Again, if the prior information is poor, it is a diffuse prior, sigma 0 square, very large, doesn't have to go even to infinity. This dominates in the denominator, and the result is a cancellation, and you end up with sigma square. So as you diminish the quality of the prior, you end up the two overlapping in terms of accuracy. Otherwise, for any finite sigma 0 square, you get a better, smaller error for the map estimator. Now, let's go to the sample mean and the sample variance and calculate these measures of quality. The sample mean, the variance of it, which really will be the standard error in estimating the mean of a bunch of random variables with common mean, and in this case common variance, they are IID. X hat ML was 1 over k sum of zj. So this is the sample mean. Now we subtract from this x0, you can see it here, brought inside the summation because there are k times, there's a division by k that takes care of it. So subtracting it once or subtracting it from each of the terms, that's really the same now because of this constant outside. And when you square, there's a k square here, each of these is a wj, and therefore when squaring you end up with the variance. No cost terms because they are independent, those noises. You have k such terms, so it's a k sigma square over k square from here, so sigma square over k. First observation is, as k goes to infinity, it converges to 0. This, as we'll see, is a property that is called consistency, that the error goes to 0, in this case the mean square error, and consequently our estimator will converge. The value it puts out will converge to the true value, and we'll discuss this in more detail later. Now, the second one. So we have the variance of the sample mean. What about the sample variance? We have a sample variance, which we are now going to look at it in a slightly simpler context, namely when the true mean is 0 and known. In this case, the maximum likelihood estimator for the sample variance is just the sum of the zj's squared divided by k. It's very easy to see. It is unbiased. There is no problem with any bias. So the next step we want to find out is the variance of the sample variance. Okay, the true value will be denoted by sigma square. So we have the expected value. This is our estimated value for the variance, sigma hat ml squared minus the true value sigma square, the whole thing squared, and expected value. So what we do is we subtract here the sigma square, and this is our sample variance. And substituting each zj is really, in this case, because the mean is 0 and known, is a wj. So what we are going to have now, first we can replace the zj's by the wj's. But we have to be careful. Here there is a summation, then square. This is really the product of two summations, and we have to change the running indices. First will be kept j, the second will be kept I. So what we have is wj squared, wi squared. These are the terms that result in the double summation, and the expectation is over these products. What's important is we have to distinguish between the cases where j is different than I versus when j is the same as I. Before doing this, we need a cross term between this and the summation. That's 2 sigma squared 1 over k, sum of the expected value of wj squared, and the last term is just sigma squared squared, sigma to the fourth, which stays as is. This is easy because this is sigma squared, k times divided by k will cancel, and here we have to be more careful. As I said, for j equal to I, we have one expression. How many times does that occur that j equal to I? For each j, there is one single I, so it happens k times. Then we have the expected value of wj to the power 4. This is the fourth moment of a Gaussian, which is 3 times sigma to the fourth. That's a zero mean Gaussian. The other cases where j different than I, then wj and wi are independent, so this gives a sigma square after expectation, this another sigma square. So it is sigma to the fourth. How many such terms we have? K times k minus 1, because we took away the k terms where I and j coincide. The remaining is k times k minus 1. So, carrying out the algebra here, the result is 2 sigma to the fourth over k. The first observation is this also converges to 0 as k goes to infinity. And here is what we used in what I discussed, the term. This is 3 sigma to the fourth, and this is just a sigma to the fourth. So, therefore, based on the result that the variance of the sample variance is sigma to the 2 sigma to the fourth over k, the standard deviation or the standard error of the sample variance is sigma square root 2 over k. So I'm using the notation here sigma sub xi as the standard error of the estimate xi, and xi is the sample variance in this case. Let's look at an interesting application. How many samples do we need to estimate the variance of a certain random variable with a given accuracy? Okay, from what we had before, we will answer the question how many samples we need to obtain the sample variance within 10% of the true value with probability 95%. Whenever you get a question of this kind, it is usually formulated in non-mathematical terms. We've got to convert the question into a mathematically meaningful question which can be answered properly. So, the given accuracy will be 10% of the true value, but then we have to say with what probability we want to get this kind of accuracy. So, with very probable, with high likelihood or high probability, we want to get a high accuracy result. So here are the two qualifiers. With high probability, we want a highly accurate result. Because remember, the output of any estimator is a random variable, so you have to qualify these things appropriately. Now, we will make an assumption, which is really an approximation, that the sample variance is normally distributed about its mean, which will be equal to the true variance because we saw it is unbiased, with standard error as above, that sigma square root 2 over k. What is the 95% confidence region of a Gaussian variable? So if we say that this is Gaussian, this is the true value, the probability that it will be 2 standard errors away, 1.96 standard errors. The estimate will be 2 such standard errors away from the mean. is 95%. So based on the Gaussian, we use what's called a 2 sigma or 95% probability region. And once we put in the two values, we can now do a simple algebraic manipulation to bring in the 10% relative error concept. Okay, so the requirement of at most 10% error in the variance estimate says sigma hat ML square minus the true value in magnitude over sigma square is 0.1. Putting it into the previous equation, we immediately find a single simple equation for K that yields 800. This is a fairly large number, as you can see, but this is what is required for the accuracy we wanted. With 95% probability, you want to be no more than 10% away from the truth. And the center limit theorem, which says that the sum of a large number of random variables is Gaussian under certain conditions, here we had independent random variables, can be applied for this number, even though the exact distribution is still not Gaussian, not quite symmetric, but reasonably close to that. A second example we are going to consider is estimation of the probability of an event. So now we are talking about a discrete occurrence. Assume that you have n independent identical experiments. In these experiments, an event occurs n0 times. We can estimate the probability of this event by p hat equal to the ratio of n0 over n. Clearly, the first observation about this estimate, which has not been justified, even though it can be derived rigorously, it is that it is an unbiased estimate because the expected value of p hat is the expected value of n0 over n. N is not random, but n0 is random because n is a number of experiments, n0 is a number of outcomes. If there is a true probability p and the expected value of the number of outcomes is cap n, the number of experiments, times the probability p. So clearly n cancels and the result is p, the true value. So conclusion number one, this is an unbiased estimator. Now, if we look at n0 is really the sum of n independent, identically distributed binary random variables, so it will have, it's really a Bernoulli variable, its distribution is given exactly by the binomial. So it's that binomial random variable. However, we can again simplify the problem by assuming that the number of experiments n is large enough in which, again, using the center limit theorem, we rely on the Gaussian approximation of the probability density function of p hat. It can be easily shown that the variance of p hat is p times 1 minus p over n. The variance of a binary random variable, again, very easy to show, is p times 1 minus p. You take n such things, divide by n, and therefore the variance is the sum of the variances over n squared. You have n such variances, so you end up with a single n in the denominator. So with this result that this is my variance, again the observation that we have here is it does tend to 0 as n goes to infinity, which means with more and more such experiments the relative frequency of the outcome of our event of interest, n0 over n, will tend to the true value p. Now, what we want is to find for a finite number the accuracy. If we use a 95% or 2 sigma confidence region, and the sigma here will be the square root of this standard error that we have, so the probability that p hat minus p in magnitude is less than 2, should be 195, it doesn't matter. 196. It's close enough to 2. Square root p times 1 minus p over n, this should be 0.95. So we want with 95% probability to be this limited in error by this. But now we don't know p. So what can we do about it? We can use a p hat, the estimated probability, instead of p in the expression of the variance above. So let's look at some numbers. Assume we make 1,000 experiments and p hat came out as 0.1. How good is it? The standard deviation of my estimate, 0.1, will be square root 0.1, 1 minus 0.1 over 1,000, which is about 0.01. What is the confidence region that we talked about, the 95% confidence region, is the 0.1 plus minus twice 0.01, which is 0.08 to 0.12. Now, to connect it to things you can read in the newspapers quite often, such techniques are commonly used in public opinion polls, but in a more conservative way. What they do is they assume that p is 0.5 because this gives the largest variance. If you look at the expression, the p times 1 minus p peaks at p equal to 0.5. So with this conservative assumption, for n equal 1,000, the standard deviation is square root half over 1,000, that's about 0.016. And therefore the confidence region is whatever you obtained, p hat minus, say, 2 of these standard errors, which is approximately 0.03, up to p plus twice that error. This is how to interpret the results from a poll, which in layman's terms say they have a margin of error of plus minus 3%. If you really want exactly 3%, you go to approximately 1,200 such experiments or such answers in the poll. The question is, in practice, you've got to be very careful to take what's called a representative sample from the population. So there are a little bit more fine points when you talk about polling, but nevertheless, this does provide the mathematical underpinning of the result, which is the margin of error. And typically what they use in calculating that margin of error is a 95% probability, even though nowhere is it stated, obviously. Another important property, which we alluded to, is consistency. Does my estimate go to the true value as I gather more and more data? Do we have convergence? And this is the consistency property. If we're talking about the estimator of a non-random parameter, we say it is a consistent estimator if the estimate, which is a random variable, converges to the true value in some stochastic sense. Using the convergence in mean square criterion, we have that the limit as k goes to infinity of the expected value of the square of the error, x hat, and now it's written out in full, function of k, the number of data points, and zk, the super k, the cumulative data set, minus the true value. So this is the mean of the square of the error. This goes to 0. This is the consistency in the mean square sense convergence, which implies we have mean square convergence. Instead of saying that the estimate converges to the true value, we can say that the error converges to 0, and then we have to say in what sense. In this case, it's a mean square convergence. Now, it's important to realize that the consistency, as we defined it here, is an asymptotic property. It is defined for when the sample size k tends to infinity and the object of estimation is a fixed parameter. You get more and more data, the parameter is sitting there just waiting to be estimated. It's not running away. However, in dynamic situations in which you encounter in most engineering problems, you have state estimation. You don't have a fixed parameter waiting to be estimated for as long as you're expecting it to stay there. It is available and unchanged. So what we have is, in dynamic situations, the object of the estimation is an evolving state. You can never estimate it perfectly in typical cases because as you get more and more data, it changes, which means it's not waiting, which means you cannot get an infinite amount of information because the older data become obsolete by the time you collect the new data, and there will be some kind of a counterpart to this. Consistency in the dynamic situation will be defined as a finite sample size property, namely you get a variance. Your variance goes to steady state as opposed to converging to zero. And what you want is for the variance to be a representative, typical, honest indication of your accuracy. So this will be the new meaning of consistency in a dynamic context. Now, having seen problems where you have convergence to zero of the variance, means the error variance is zero, the estimate goes to the true value. What we are interested in is general results that will indicate how fast this can happen. And it turns out there is a result due to Kramer and Rao that gives you a lower bound on the variance of an estimator. So, according to the Kramer-Rao lower bound, the mean square error, or the variance, corresponding to the estimate of a parameter cannot be smaller than a certain quantity related to the Likert function. And that quantity, turns out, it's called the information matrix. So what we have is the following result indicated for a scalar case. If we are now in the business of estimating a scalar non-random, that's a fixed parameter, x, and we have an unbiased estimator, x hat of z, the variance associated with this estimator is bounded from below as follows. Expected value of the square of the error is greater or equal to the inverse of a quantity j. Now, j, turns out, is either the negative of the expected value of the second partial of the log likelihood function. And remember, the log likelihood function is the log of lambda of x, which is, lambda x is p of z given x. Z is the total data set. So, there's a second expression for this quantity called Fisher information, is the expected value of the square of the first partial of the log of the likelihood function. Remember, it's important that these have to be evaluated at the true value of the parameter of interest. Now, given this, if you have an estimator and its variance is equal to the Kramer-Rao lower bound, then such an estimator is called efficient. There is nothing better than it. In principle, what the Kramer-Rao lower bound tells you, you cannot beat this variance. It's the utmost minimum you can obtain. In some problems you can obtain that minimum, then you are efficient. In other problems you cannot get to that minimum, you are not quite efficient. So this is called statistical efficiency. And it's very important because this is a very general result. There is a multidimensional counterpart. If you have non-random vector parameters, the Kramer-Rao lower bound states the following. The covariance matrix of an unbiased estimator is bounded from below as follows. Expected value, x hat z, that's a vector, minus x0 is a vector, column form. Take the same thing in a row vector form, after transposition becomes a row, so this is a square matrix. The expected value of this, which is the covariance matrix of my error or of my estimate, whichever you want, because the error is 0 mean and the estimate has this mean equal to x0, is greater or equal to the inverse of a quantity, again denoted by J, but now J is the Fisher information matrix, FIM or FIM, and J is the negative or the expected value of the gradient with respect to x times the transpose of this gradient log likelihood function. This is a second derivative vector version. The result is a matrix because this is a column vector, this is a row vector, this is a scalar. Or is the expected value of this column vector the first derivative, the gradient of log likelihood function times its transpose. So column, row, again, it's a matrix, and the whole thing after expectation has to be validated at x equal to the true value. We have an inequality here which has to be interpreted as follows. A matrix A is said to be greater or equal to B if and only if, or equivalently, if the difference C defined as A minus B is positive semi-definite. So this is the interpretation of an inequality between two matrices. Their difference is positive semi-definite. If this is a partial inequality, if it was a strict inequality, which is not the case here, then the requirement would have been positive definite. So, a couple of remarks. You can look at the Fisher information matrix, which is the lower bound on the covariance matrix or the variance of your estimator, as a quantification of the maximum existing information in the data about the parameter. This is a consequence of the likelihood function, and the resulting expression from the bound that we have seen, the expected value of the partial derivatives and so on, or gradient, is going to be indicating how much information is in the data about the parameter. Efficiency amounts to the statement that the extracted information is equal to the existing one. Namely, all the information in the data has been extracted. This is a very important result. A necessary condition for an estimator to be consistent. Consistency, remember, means that the estimate converges to the true value, or the estimator error converges to 0. So consistency in mean square is that there must be an increasing amount of information, again in the sense of Fisher, about the parameter in the measurements. The Fisher information has to tend to infinity as k goes to infinity. If you are bounded from below by the inverse of j, if you want to converge to 0, you have to make sure that j goes to infinity, because you cannot be below j inverse. If j inverse goes to 0, if j goes to infinity, then j inverse goes to 0, then you have a chance of converging also along that. Otherwise, you have to stay above 0. So the variance converges to 0, or can converge to 0, if the Fisher information tends to infinity. If you have an infinite amount of information, you can extract, and you can extract it all, you can converge to 0. If you have a finite amount of information, no matter how well you do, you can never get variance going to 0. Let's take an example. And this will show a simple estimator that is efficient. We'll look at the likelihood function for the estimation of the mean x from a set of k IID measurements with Gaussian noises. The Fisher information in this case is a scalar quantity. The log likelihood function is just the sum of the squares between z and x. that simple linear measurement model. Take the second partial, suggest that you go through the detailed calculations. Turns out to be, after taking the expected value, k over sigma square. Thus, what we have is, according to the Camera lower bound, the mean square or the variance of my estimator is greater or equal to J inverse, which is sigma square over k. Well, if we look at the equation indicated here, where we have already derived the actual variance of our estimator, it was exactly the same, which means the actual variance is the same as the bound, namely the maximum likelihood estimator, which in this case is the sample mean, is efficient. Our condition of equality in the Camera lower bound is satisfied. Furthermore, this bound also goes to 0. For every k is efficient, for k going to infinity, it converges to 0, and my actual variance converges to 0 at the same rate because the two are equal. So what we have is a nice result that for this simple linear Gaussian problem, we have an efficient and consistent estimator. We do as well as you can ever dream, and we end up with a correct result asymptotically. Some of the large sample properties of the maximum likelihood estimator will be just listed because they are more difficult to prove. First, the ML estimator is asymptotically unbiased and asymptotically efficient. There are some regularity conditions for the likelihood function for this to hold. So what we observe is the following. If there is enough information in the measurements, in which case the Camera lower bound will tend to 0, the variance of the ML estimate will also converge to 0. That's because of the efficiency. Therefore, the maximum likelihood estimate will converge to the true value. It will be consistent. Another property of the maximum likelihood estimator is that it is asymptotically Gaussian. So, what can we do with these properties? If we combine all these, we say the following. The maximum likelihood estimate is asymptotically Gaussian with the mean equal to the true value from the parameter I'm estimating, and variance given by the CRLB. This can be summarized for a vector parameter as follows. X hat ML, the maximum likelihood estimator for the vector x based on k observations. For large k is Gaussian with mean equal to the true value and covariance matrix given by the inverse of the Fisher information matrix. It's not indicated here, but J is obviously a function of k. So, this is important because there are some problems, and we'll see one of them of practical engineering significance, where you have a complicated estimator. You cannot calculate its variance because it has to be obtained numerically, but you can calculate the Camera lower bound. And if you know that asymptotically you meet the bound, you can use the bound as your covariance. So this is the value of this result. To summarize, what we have seen is that the estimator of a parameter is a function of the measurements that yields a best approximation for the value of the parameter. The estimate of a parameter is the value taken by the estimator function for given values or realizations of the measurements. We covered the two models for the parameters to be estimated. Unknown constant or non-random is the first one. The second one is random, in which case we have a single realization of a random variable according to a certain prior PDF. The second model yields the Bayesian approach, while the first model leads to what is called the non-Bayesian approach. Non-Bayesian approach, we can see the Likert function approach, the least squares approach. Bayesian approach, we had a maximum a posteriori map approach and the minimum mean square error approach. And here are these concepts. The Likert function for a non-random parameter is the PDF of the measurements conditioned on the parameter. Remember, the Likert belongs to the parameter, not to the measurements. It's of the parameter if you have those measurements. Bayes' formula allows us, starting from a prior probability density function of a random parameter, to obtain its posterior or conditional PDF given the measurements. The maximum likelihood estimate, which pertains to a non-random parameter, is the value of the parameter that maximizes its Likert function, which is again the PDF of the measurements given the parameter. The maximum a posteriori estimate or map, which pertains to a random parameter, is the value of the parameter that maximizes its posterior or conditional PDF. So that's the P of x given z. Its maximum is this. The maximum of P of z given x is the ML estimate. The nice thing about the two, map and ML, are that the map estimate of a parameter with a diffuse or non-informative prior will coincide or degenerate into the maximum likelihood estimate. And that's intuitively very pleasing to know that you can make a prior assumption, then get rid of it by making it non-informative. The least squares estimate, which pertains to a non-random parameter, is the one that minimizes the sum of the squares of the errors between the measurements, the observation, and the function we observe, which is a function of the parameter. So that's a least squares fit of the measurements to the parameter. The minimum mean square error estimate, which pertains to a random parameter, is the one that minimizes the expected value, the mean of the square of the parameter estimation error conditioned on the measurements. So mean, minimum mean square error, you can see the words here in the text. Now this estimate turns out to be the conditional mean of the parameter given the measurements. So you calculate the posterior or conditional density and take its expected value. If in a given set of measurements the errors are additive, zero mean and Gaussian and independent, then the least squares estimate coincides with the maximum likelihood estimate. The map estimate of a Gaussian random variable will coincide with its MMSE estimate, the conditional mean, because again the Gaussian density is unimodal, has a single peak, and it's symmetric. The properties of estimators we covered: unbiasedness. If the mean of the error is zero, the variance or mean square of an estimator is the expected value of the square of the estimation error for an estimator. The variance of an estimator of a parameter modeled as random is smaller than when it is modeled as an unknown constant due to the prior. If the prior is informative, being some kind of information, obviously using it should give and does give, indeed, better results. An estimator consistent, that is called consistent if the corresponding error converges to zero. In some stochastic sense, the most common is in mean square, the other in probability, with probability 1, which are discussed in more specialized, more advanced probability courses. The Cramér lower bound is a lower bound on the achievable variance in the estimation of a parameter. If we have an unbiased estimator, it is given by the inverse of the Fisher information matrix, and this gives us the FIM, quantifies the existing total information about the parameter of interest in our observations. Finally, an estimator is called efficient if its variance meets the Cramér lower bound. In other words, if all the existing information has been extracted. A few words on the terminology you will find in the literature or at other occasions where you hear people talking. In most of the literature, there is little or no distinction between the terms least squares and minimum mean square error estimation. We are trying to be a little bit more pedantic. The MMSE estimation is sometimes called LS, least squares, which is incorrect according to our definition because this is Bayesian, this is non-Bayesian. It is also called least mean square LMS, which is a valid alternate designation. And sometimes it is called minimum variance. Just so you are not surprised that the language is a little bit inconsistent.